Welcome to Lecture 11 on Robot Arm Kinematics. In this chapter, we'll be learning about forward kinematics and inverse kinematics. Forward kinematics is a process where we begin by assigning reference frames for in locations or to define locations. So for example, in this one link robot, we would have two reference frames. One here, one XY frame here at the base, and another frame here at the end effector. And one of the things we're going to be very interested in doing is getting transformations of one frame with respect to another. So, for example, we might want to know what is the transformation of this end effector frame with respect to the base. And that transformation would be defined by a rotation about Q1, and that rotation would be described by this rotation matrix about the z-axis by a Q1 angle, followed by a translation along this axis by an amount of A1, which could be represented by this matrix. And in totality, we could represent that transformation by a single matrix in this way, where the translation would be represented by this amount with respect to the base. And forward kinematics is really asking the question of, given a set of joint angles, for example, the joint angle Q1, what is the end effector pose? That is, what's the orientation and the position of this frame with respect to this one? The second aspect of the chapter deals with inverse kinematics. This is the inverse problem. So now, given an end effector pose, that would be an XY location here, and an orientation with respect to the base, what are the robot joint angles? The inverse kinematic problem is more difficult than the forward kinematics. And in fact, there are multiple approaches to solve this problem. For example, on this side, we can see a geometrical approach that is based on the law of sines and the law of cosines. So here, if we have the X and Y location, then we can extract the Q1 and the Q2 angles. One caveat or warning is that sometimes we can have no solutions, multiple solutions, or an infinite number of solutions when we have redundancy. Or for 6 degrees of freedom space, if we have more than 6 degrees of freedoms in a robot, we can have this infinite number of solutions. And this simple representation, we can have what we call the elbow down solution, but we could also have an elbow up solution where the first link actually has an angle approximately like this and then coming back over here. Other approaches include the algebraic method and the numeric method. In our chapter, we will look at geometric and algebraic solutions and then refer you to packages that also do numeric solutions. All of them have their own strengths and weaknesses. Having said that, let me introduce some of the kinematic packages in ROS. The first one I'll mention is one of the oldest one called KDL. It stands for the Kinematics and Dynamics Library. This is a numeric solver, and it can compute both kinematics and dynamics. At its foundation, the library extracts the kinematic chain from the URDF file on the ROS parameter server, and then it's able to create a solver object that can do both forward kinematics and Jacobians between frames. Inverse kinematics can be done, but are not always handled so well. For 6 degrees of freedom robots with spherical wrists, it's stable and can find solutions. For redundant robots with no spherical wrists, you may not have a solution. And sometimes even for the 6 degree or 7 degree of freedom robot with spherical wrist, solutions may not be computed in time. An alternative package more popular in recent years is TrackIK. This is a numeric solution as well. It's similar to KDL, but it has been optimized, so it provides faster responses and also has increased accuracy. You can click on these two links to find more information. A third package is called IKFast. This is an analytical solution. It is a powerful IK solver based on Rosen-Diakonov's OpenRave, and the package can analytically solve kinematic equations for any complex chain. So this is powerful because you can define any chain, 3, 4, 5, 6, 7 or more degrees of freedom, and get an analytic solution that is extremely stable and fast. Lastly, we have self-derived kinematics. It may be that you have your own robot and devise an analytic or geometrical derivation, and so you can compute the forward and inverse kinematics through that approach. When we compute forward kinematics, we'll often be using Derived-Hardenberg parameters and conventions, which I'll briefly introduce next. So section 12.1 will introduce forward kinematics. In particular, we'll look at the process in which we present an analytic solution for forward kinematics, or DH parameter solution, for forward kinematics and ROS using DH parameters. To start off our experimental setup, we're going to be using the standard Gazebo RRBot tutorial. This is a 3-link and 2 Fwd joint robot, and this can be easily loaded by launching Gazebo with an empty world and then ROS launch rbot.launch. Here you can see the Gazebo and the RVis representation of the robot. Now, I mentioned earlier that Derived-Hardenberg's conventions are important for forward kinematics. You can find this video at the YouTube or Yoku link down here, and I'd like to play it right here for you so that you can get an idea of what DH conventions are.
Derived-Hardenberg parameters allow you to succinctly describe the motion of a series of rigid joints. This is useful for efficient calculation of forward and inverse kinematics. The process begins by defining the z-axis along the axis of rotation for Fwd joints, or the axis of translation for prismatic joints. Since this is the first joint, the x-axis is a free choice. For later joints, each x-axis will point away from the previous joint. The y-axis simply completes the right-handed reference frame. Now, if we add another joint, we can determine the transformation between them. As before, the z-axis points along the axis of rotation. The DH parameters will be derived from the common normal between these z-axes. The common normal is orthogonal to both vectors, and is also the shortest line between them. The new x-axis points along the common normal, and has its origin at the intersection with the new z-axis. Notice the origin is not within the physical actuator, because the DH parameters are only concerned with the motion of the links, not the physical placement of components. Using this protocol for laying out the reference frames, only 4 parameters are needed. The first of these, d, is the depth along the previous joint's z-axis, from the origin to the common normal. Theta rotates about the previous z-axis to align the x-axes. R is the length of the common normal itself. Most texts call this parameter A, which is unfortunately easy to confuse with alpha. Instead, calling it R is a useful mnemonic, as this is also the radius of revolution for the new origin about the previous z. Finally, alpha rotates about the new x-axis to bring z into alignment with the axis of joint motion. Now there's one special case, when the z-axes are parallel. Because parallel lines have an infinite number of common normals, you can choose any d value you like in order to place the new origin at a convenient location, such as the center of a link or the tip of an end effector. The other parameters are the same as before. Theta rotates about z to align the x-axis with the normal, and r translates out along the normal to reach the new origin. Alpha is already known to be 0 in this case, since the z-axes must be parallel for this to apply, thus no rotation is needed. Congratulations, that's all there is to it.
Basically, we come here to the sacro file for our bot.sacro. We can open it quickly over here. Okay, and so you'll be seeing that we have this kind of file over here, and we're going to set joint 1 continuous, linking link 1 and link 2. Here the origin has an equation that we haven't seen before in this book. X is equal to height 1 minus axis offset, and then we have a width here too. But this is a key line where we say, hey, let's set this frame of reference to be aligned with the z direction of the joint. Okay, so this is setting a URDF file to follow the DH parameter conventions. This is not typically done. But this is a way that our book is helping us to understand how do we do DH for kinematic computation if we want to use Ross. So you would have to do something like this. Okay. It's also useful to define a frame of interest at the tip of the last link, because we don't have a joint there, but we want to know the tooltip position. So to do that, we need to introduce a fictitious or a fake static joint. That's not going to be a true joint, right? There's not going to be an extra link at the end, but we need a joint there for the purposes of computing the forward kinematics. So I'll show you the code in a second, but when we do that, we can use TF, we can use KDL, we can use TRIK, or we can use the code we're going to do here to compute transformations. So here's a fake or fictitious joint. We call it the Flange Joint, and it's going to be fixed. And we have this parent link as link 3. We have a child link Flange, and it's just there. And that's going to help us compute the kinematics. And then we have this link Flange. It's connected to the static joint, right? But this link, again, shouldn't be there. So we do not define any inertial, any visual, or any collision components, because it's like also a link that should not be there. So it has nothing. It has no mass. It has no inertia. You cannot visualize it. It has no collision. Okay? And it's a technique that we also used earlier to model mounted sensors, right? We introduce fictitious joints. We set the joint limits equal to each other, and then we were able to introduce a sensor. We looked at that last week. Oh, here's the video. So if you want more details on forward kinematics, I like Professor Peter Cork's lessons, and you can go to his website to find more. Recently, his institute has opened the Open Online Robotics Education website, where a number of robotic courses are available for everyone for free. Okay, so once we have set up the sacro model this way, we need to start using building the DH parameters to then get the forward kinematics. So from this particular RR-bot example, we can have this header file rbotkinematics.h. What we're going to have in this file is have a definition of the Denevit-Hardenberg parameters. So we have our A's, we have our D's, and we have our alphas. So here in the D's, for example, we have an offset of 0.1 from the base to the first joint. Yeah, from frame 0 to frame 1. The last one is 0 because it's the offset from frame 1 to the flange. And this is the distance of the link. So we have two links, 0.9, 0.95, and there's no change in alphas here. Going from URDF to DH models, it can be confusing. Okay, so you need to properly draw out your robot, what it looks like, the frames of reference. Here the z-axes are parallel to each other. So let's go back to see that robot right here. So you'd see that the z-axis here would be parallel to this one. That's right? So here the alpha angles are set to 0. The A parameters are the link lengths, and the D1 is the offset along Z from link 1 to link 2. Okay, so we get that set up. And so then we have this rbot forward kinematic invert kinematics.cpp file, and uses this compiles a library that can be used to compute forward and inverse kinematics. This file depends on the DH parameters and the header file from before. We'll take a look, or you can take a look. I've included in the slides here today. So the primary method of this file is called compute A of DH. This A is the transformation matrix. In other textbooks, this can often be the T, the transformation matrix from one frame to the next. So what's the output, or what does this method return? It returns a transformation matrix. This has to be a 4x4 matrix. If you're not familiar with the class, this 4x4 includes a 3x3 rotation matrix and a 3x1 translation matrix for the 3D example. Okay? We'll look at the code in a second. And so it's a coordinate transform between the DH frames. So here is the code. So here's compute A of DH. We're going to get this A out, and what we're going to put in is we need the rotation matrix and we need the translation. So if you see the arguments here, we have the joint angles, we have the A parameters, the D parameters, and the alpha parameters of the DH parameter set. This is going to be our output A, the transformation matrix, but we also need to create a 3x3 rotation matrix and a 3x1 vector. Okay, so here we create the instance, then here we need to set the size. For now, we set them to be identity matrices, 4x4, 3x3. Here we summarize the computation of cosines and sines of q's, CQ and SQ, and also for alpha. And because here we simply have two joints, we're going to have this R00, R01, R02, and then just R10, R11, R12. So we have a 2x3. We have a 2x3. Okay? We have two joints, so we have a 2x3. And, sorry, let me see. No, we have, let me, three by three, sorry. This one is done by default. We don't need to do it. It's 3-1. And so here we have, let's see, this is, oh, sorry, this is going down the columns. Now, if you feel confused about these values, you need to go back and study DH parameter conventions. Okay, these are just rotation matrices with some assumptions. This is going down the column 1, column 2, and then column 3. I think this this should be 2, 3. Let me see. or 2, 0, 2, 1, 2, 2. It would be best to draw it out to get here. And finally, this is the translation, okay? A times a cosine, A times a sine, and D here. So basically, then we can use this method from Eigen. Eigen, by the way, is a very useful linear algebra C++ library, right? So you can say, you can simply do something like this. A dot block 3, 3, starting from 0, 0 is equal to R. So this copies R onto the 3 by 3 block starting at 0, 0 on the top left of A, and then you can say, hey, let's take the third column of A, starting from the top, and then set P equal to that. So this is a way to copy R and P over to A, and then we return A. So what does this code do is takes a set of Derived-Hardenberg parameters. Those parameters come from 2 successive frames. So you have 2 successive frames, you get those parameters, you get the transformation matrix out, right? So then if you want to do the whole robot, we need to do consecutive pairs of joints, or frames, I should say. So for example, if you want to know the transformation from the base to the flange, or to the endpoint, right? You first would compute the transformation A from 0 to 1, and then from 1 to the flange. So in this same code, we have this method called FwdKins solver. Okay, this is the name of the function. And here we're going to be taking the A's. Let's see. Let me see. This is CVEC. Here's our what do you call it? At the beginning, empty A matrix. This is what we're going to use to compute the final base to flange transformation. And then we have the intermediate transformation here, A from I to I from I minus I. Okay? This is like we're going to do 0 to 1 here, rotation matrix, and translation. So this for loop is going to go from 0 to the number of joints. So it's maybe like considering from here to here, and then from here to here, and then from here to here. So we call compute A of DH. We provide the joint angles here, DH parameters here, DHA parameters, DHD parameters, DH alpha parameters. And here we do a simple copy. We take the transformation AI minus I, which corresponds here first to I equals 0, then to I equals 1, and then save it here in A mats. So at the end, what we need to do is simply multiply them together. If you have a base link with respect to the world, maybe a link that's out here outside of the robot, you include that and multiply that by the frame 1 with respect to the base link. And so that would give you from frame 1 to world. Okay? So here's base link with respect to world, and then A mats 0. This is just from the base to an external link. Okay? And that's the first one. So that's just 0. There's no for loop here. After that, we have a for loop, again, that starts from 1 to the number of joints. And that says A mat product starting from I, which is equal to 1, is A mat products, matrix products A minus 1 times A matrix I. Okay? So this is, the 0 here is world to base. And then here is base to 1, 1 to 2. All right? So this equation up here is what you would see down here. I might add another term here, maybe that says A base to 0. And that's what this line is doing. So after that, we can just return the A matrix products, decrease the number of joints by 1, and that's going to give you the tool flange frame, or the final transformation. So this code that we have right here can be used to compute the forward kinematics of a lot of these robots. A 6 degree of freedom ABB robot, or a UR-10, or a Baxter arm, or some NASA satellite servicer arm. If you're going to use different robots, the only thing that needs to change is you need to define the number of joints, 6 or 7, and the values of the DH parameters. Yeah? If you do that, then you can run that code very easily. If we were to use KDL, we don't need to use all this stuff. We don't need to derive the DH parameters ourselves, because we can extract the tree easily from the parameter server. Okay? But we still want to do it to test the derivation. So here's a simple example. We're going to start gazebo, then the RBot, and then we're going to run the test RBot forward kinematics. We're going to use RQT GUI to move the robot arm to some position, and then we're going to use, so after we move the arm, this node, test RBot forward kinematics, is going to give us the transformation from the base to the flange. Yeah? And we need to compare that with the result that comes out of TF Echo. TF Echo is a ROS built-in program that gives us transformations between links. So here we can say, hey, what's the transformation between the world and the flange? And those results should be the same. Okay? So let's try to open this. Sorry, let me close this. Okay, so we start by loading the robot. Okay, here it is. And we also want to, so here run the forward kinematics. So, for example, if we start looking here, you can see that this node is printing a number right here. And this number is the transformation. So it's saying, hey, there's no displacement in the x-axis, there's a negative displacement in the y-axis, and then there's a positive displacement in the z-axis. Okay, so we can also open our viz to see, hey, where's the x-axis, where's the y-axis, where's the z-axis? Okay, and this is the rotation matrix right here. So now let's open RQT GUI. Let me close that, and let's delete these. And then we can try to send something. Oh, let me see, what is this one? RBot joint 1 position controller, command, joint 2, must be this one. Is this the right one? Message publisher. Oh, cannot get it. Oh, here it is, sorry. Controller command, here's the type. Frequency, we might do that. Okay. and then data. And so expression, we might say move to 1, but we're not going to activate that yet. And the last thing we're going to do is also run tf echo world flange. So we're going to look at this transformation. Okay, let me make that a little bit smaller. Okay, and then we're going to, let's do this. We want this window to be large as well. So we're going to be comparing basically these two windows, right? And right now we're looking at this number, and we're looking at this number. So here the translation is 0, negative 0.2, 3.8, and here it's the same number, right? So it's saying that the code that we are currently using, our forward kinematics code based on Derived-Hardenberg parameters, is giving you the same result that TF is using. Okay, so it says it's accurate. So it says our derivation is correct. Let's move this robot over here and use RQT GUI to command the robot to some location. Okay, so here I activate this. The arm moves. Our code updates, negative 0.88, 0.2, 3.29. Same as here. Do you see that? Okay, so that's the comparison of our code and the way that we're doing forward kinematics. Again, if you use KDL or even TrackIK, you wouldn't need to do this derivation, which is complicated, and also the modification of the URDF. But it's useful for you to see how this can be done. Okay? Part of your homework for this part will be running TrackIK to compute forward kinematics. Yeah, should be very straightforward. Okay, almost finished. We just want to try this one more time, but then do it with a 6 degree of freedom robot. Okay, so here we have this IRB 120 forward kinematics, inverse kinematics test. These files are also computing inverse kinematics, though we haven't discussed that yet. And so the difference between this file and the previous one is we have different number of joints, and we have different set of DH parameters for this robot. Everything else is the same. The main loop is the same, computing the transformations iteratively. Okay, so let's try this code. Okay, let me close this. This will be link 7. This will be the same RQT GUI. Yep. This one will be RB 120. That's the name of the robot, of the model, yeah. RB 120 description. Launch, and finally gazebo. Okay, so we're opening gazebo. Here, take this off. We launch the robot. Okay, there it is. Okay, so this is a industrial ABB robot. Okay. We start the forward kinematics, inverse kinematics node. And so let's see what we have here. This is the rotation matrix here. And this is the transformation here. Okay, just looking at forward kinematics. Okay, let's run TF down here. So here we get 3950.533. So here we get 3949. This is 0 to the minus 10, 0.533. Okay, so let's use RQT GUI, and we can command a few things. Let's delete this one. And so here we have a bunch of them. We have joint 1. Maybe let's set these frequency 10. Add that one. We can do joint 2. Add that one. We can do joint 3. Command. Add that one. We can do joint 4, 5, 6. There it is. Right now these are set to 0. Yeah, and so again, you would be comparing this location with this location. So here we have 6 to 4, 6 to 4. Maybe move it 90 degrees. Yeah. So what changes? You know, the height is the same, but now x is almost 0, and instead y is 3.7, right? So here we can move it down, maybe -1. Oh, that was moving it back. Let's change it to 1. Okay, so we move like that. Might have been a collision. So here we're getting 485, 1511, 485, 1514 about. So that's updating. There's a 1514 and then 15.1. Yep. So very similar, right? And so you can just play around, keep moving this. This is a rotation, 90 degrees. Oh, no, yeah, what happened there? Let's see. That was not a rotation. That was, oh, I'm sorry, it was a rotation, but not the one that I expected. That's this one, so maybe -1. .57, we have that rotation. Okay, so now we have those position controllers. We're moving the robot, and basically we see that we're still getting similar results. Let me see what happened here. So here is -0.06, like this one, 0.57, 0.57, 0.496, 0.496. Okay, so it's what we're doing here is really trying to go down to mathematical models for forward kinematics with the H parameters, modify the Sacra file, and then code it in C++. Okay. So again, in your homework, you'll do something much simpler, just using KDL or TriGuideK. They have the same API, basically, and you do this. So, but now, this is a simpler problem, and we often won't need to use forward kinematics directly. What we will need to do is inverse kinematics, because when we need to grab an object, we need to know the joint angles for that position. Okay, so next week, we'll look at inverse kinematics, and a little bit more on motion planning, and then we'll finally move to actually grabbing the objects. Okay? Thank you very much.